Now we're going to look at conic sections that are not centered at the origin. So we'll use HK to represent the center of the conic, or the vertex if we're talking about a parabola. So the equations for an ellipse centered at HK, of course this depends on whether the ellipse runs horizontally or vertically. Notice these equations are basically what we looked at in the last section, only now we have minus h connected to the x term, so x minus h squared, y minus k squared. H is always associated with x and k is always associated with y in these equations. So if a squared is bigger than b squared in both of these equations, and then that will correspond to the orientation of the major axis. So that's all the same as before. So in the first case, the major axis is horizontal. In the second case, it's vertical. The equation to find the foci is still the same. It's only the c, you count along the major axis from the center of the ellipse, which is no longer 0, 0. So if you understand all the relationships that we talked about last time, this is pretty easy, just changing your center. Otherwise, there's really nothing new to remember. So in this one, first example, x plus 4 squared would correspond to h being negative 4. Notice these are both subtraction here. So we take the opposite signs, negative 4. And y minus 3 squared would mean k is 3. So the center is negative 4, 3. That's all similar to when you graph circles back in college algebra, right? Same idea. And then the major axis is vertical because this 16 is bigger than 9. And we'll just count, to find the vertices of the ellipse, count plus or minus 4 units from the center. So one vertex is here, 4 units to the right, and then 4 units to the left is the other vertex. So I would just graph it and then look at the coordinates. So that's 0, 3. Sorry, I should have put vertices instead of vertex. Vertices for plural, right? Whoops. 0, 3, and the other one is negative 8, 3. Then if we're going to graph, we'll use the other points on the ellipse found by taking this square root of 9 is 3. So we go up 3, down 3, and then we get 4 points on the ellipse. And then we need to find the foci. So we use c squared is 16 minus 9, which is 7, which implies c is equal to the square root of 7. So you need to count from the center, square root of 7 to the right and to the left was a little bit bigger than 2. So the foci would be, just estimating about here. For the coordinates for the foci, notice the y-coordinate is the same, right? That's the same for the vertices and the foci and the center. For the x-coordinates, we can just go from the center, which is negative 4, the x-coordinate of that, and then add and subtract the square root of 7 from that. Those are our two x-coordinates, and then the y-coordinates are the same, 3. So you can write that as 1. If this were a whole number, like if I knew c was 2, then I would write 2 separate values, right? I would do, if it's 2, then we'd have negative 2, 3, and negative 6, 3. Just like I did with the vertices. I'd write them separately in that case. But since this is an irrational number, I want to leave it as in exact form. If I approximated, then I'd write 2 separate points. Okay, so we're done with that one. Now we're going to actually find the center when the equation is in expanded form. So what I mean is, like in this formula here, this is in standard form. If I cleared the fractions and then squared each of these binomials, I'd get what's called expanded form. I'm not going to actually run through that, but if we do that, we'll get an x squared term, a y squared term, an x term, a y term, and a constant term. So this is expanded form. Also general form, you know, would be expanded is just saying, meaning the squares are expanded. Okay, so you're told this is an ellipse, but how would you really recognize that this equation is an ellipse? Well, the clues would be that there's an x squared and a y squared term. The other clue is that they both have the same sign. So x squared, y squared terms have the same sign. If they don't have the same sign, then it's in a hyperbola instead. Because in the hyperbola equation, remember, there's the subtraction. One term's positive and one's negative. So x squared and y squared terms have the same sign. The other thing to notice is that they have different coefficients. If they have the same coefficient, then it's actually a circle and not an ellipse. So this is an ellipse. Those are the things to look for. We'll talk more about that a little bit later. All right, so how are we going to do this? Well, it works a lot like completing the square when we found the center of a circle back in college algebra. Basically the same idea. It's just a little harder because the coefficients on the x squared and the y squared terms are not 1 like they are in a circle, right? So what we do is we group the x terms just like we do when we work with a circle. And then we group the y terms. And we move the constant to the other side. So 56 on the other side. Next, we want to complete the square. So recall when we complete the square, we use x squared plus, so we want to start with an x squared term that has a 1 in front, and then whatever our coefficient is on the middle term, we're going to call it b. So you take b, you divide it by 2, or cut it in half, in other words, and then you square that, and that gives us a perfect square. For example, if we have x squared plus, let's say, 20x, b is 20. So take 20 divided by 2 and you get 10. I'll write it out like this. Oops, divided by 2. And then you square it, and then you get x squared plus 20x plus 10 squared is 100. I didn't need the parenthesis. And that's a perfect square because now this factors as x plus 10 squared, right? X plus 10 times x plus 10. Perfect square because the two factors are the same, x plus 10 squared. Okay, so take whatever this is, divide it by 2 and square it. For this to work, this needs to be a 1. So we need to go over here and get 1s in front of the x squared term and the y squared term. If these are the same coefficient, like if these are both 25, we can just divide everything by 25. Again, then it's a circle. Since they're different, we can't get a 1 in both spots at the same time. So what we do instead of dividing, like we do when we complete the square in other situations, is we factor. So we factor the 25 out of the x terms, and then we get x squared minus 2x in the parentheses. And then we factor the 9 out of the y terms, so whatever that coefficient is gets factored out. And we get 9y squared plus 8y in the parentheses. Next, we complete the square inside each set of parentheses. So x squared minus 2x plus Take -2 and divide it by 2, and you get -1. And then in the next set of parentheses with the y's, y squared plus 8y, to take 8, divide it by 2, and you get 4, and then you square that number, and so of course we'll get 16. Now, what happens is, actually I think what I'm going to do here, I'm going to make this, just go ahead and evaluate. This is 1. And that's a perfect square now, and then this is 16. What happens now is this is not, as written, is not equivalent to what we started with because I added some numbers to one side and not to the other side. So what we have to do is balance the equation. If we're going to add these numbers here, we need to add them over here. The problem is I didn't really add just 1 to this side. I added 25 times 1, which is 25. And so I need to add 25 to this side to balance this part. Then here, I didn't add just 16, I added 9 times 16, which is, what is that, 16 times, 144, right? Yeah, 144. So I need to add 144 over here. That keeps the equation balanced because you want to make sure every step is equivalent to the step before. So now, this will factor, because it's a perfect square, it's x minus 1 squared, right? You need negative because of the -2 here, plus, and then we have a 9, and this is y plus 4 squared, and that equals, let me use my calculator for the other side, 56 plus 25 plus 144 is 225. Now the last step is to divide by whatever this number is to get our 1 over here. Remember, we need a 1, so I'm going to divide everything by 225. And 9 times 25 is 225, so this will cancel. We'll get x minus 1 squared over 9 plus y plus 4 squared over 25 equals 1. So it's just asking for the center, but if I were to graph this, the major axis is vertical because the 25 is the bigger number and is paired with y. The center is 1, -4. Right? The graph would start at 1, -4, count up and down 5 units, and then left and right 3 units, excuse me, and then connect the 4 points to get a graph of our ellipse. Don't forget to take opposites here. This is a -1, so that becomes 1. A +4 becomes -4 in the center. So it shifts the opposite way. Okay, now let's look at hyperbolas. Hyperbolas, this works very much the same way. If you understand how to graph a hyperbola centered at the origin, you just, move from the center instead. So here are 2 equations, and again, in hyperbolas, the a squared and b squared can have any relationship. They could be equal. One could be bigger than the other in either way. The way that you determine where the transverse axis runs is by looking at which term has the positive. So in this equation, the transverse axis is horizontal because x is the positive term. In this one, y is the positive term, so now it's vertical instead of horizontal. Otherwise, the lengths of the conjugate and the transverse axis, that's all the same. Where the foci are, you just count from the center. So don't worry so much about memorizing these things. It's just all counting from the center if you know the relationship from when it was centered at the origin. I wouldn't even focus on using these formulas. Just count. We'll do an example. Then when it comes to the asymptotes, one thing that is different, of course, is now the lines don't go through the origin, so they do have a y-intercept that's not equal to 0. That's an easy fix if we just use point-slope form. We can just, and that's what I would recommend you do. So the center is hk, right? So for the asymptotes, use point slope form. I have that down here in the last bullet as well, but let's review what that is. So the point slope form is y minus y1 equals m times x minus x1, where x1, y1 is a point on the line. Well, the point on the line that you'll know is the center. So adjust that accordingly for the center. And I'll write it down here now. We'd have y minus k equals m times x minus h. So put your hk in here. H is always paired with x, k with y. And then the slope you find just by counting like we did before, right? And that'll be plus or minus, because one will have a positive slope and one will have a negative slope. And like I said, you can, and in fact, you should leave the lines in point slope form. You don't need to change to slope intercept form. All right, so let's do an example. The first, oh, sorry, I guess we're only going to do one example. This example is in expanded form, or in other words, general form. We need to get it in standard form. And so we want to get this or this. So if you look at the terms here, notice the x squared and the y squared term have opposite signs. That's how you know it's a hyperbola. This can be a 9 and this can be a negative 9. It's still a hyperbola. It doesn't matter if they're the same size. What matters is their opposite signs. So this process will work just like it does with the ellipse. We'll group the x terms, group the y terms, and then factor and complete the square. So in the x squared terms, those are already grouped. I just need to factor the 9 out. And in the y squared terms, I'll need to take out negative 16. So I take out negative 16, now I've got y squared. This will become plus 2 because I'm taking the negative out as well. So be careful with that. Now I'm going to complete the square in the parentheses. So x squared minus 8x, negative 8 divided by 2 is negative 4, and negative 4 squared is positive 16. This last term should always be a positive, right? Because you're squaring something. And then in the y squared term, parentheses, 2 divided by 2 is 1, and 1 squared is 1. So now I need to balance the equation, right? Whatever I added over here, I need to add over here. So I did not just add 16 here, I did 9 times 16, which is 144. So add 144. And then with this one, I added negative 16 times 1 is negative 16. So I actually subtracted 16. That means I need to do the same thing to the other side as well. So now I'm going to go ahead and factor on the left. X squared minus 8x plus 16 is x minus 4 squared. And then minus 16 times y squared plus 2y plus 1 is y plus 1 squared. And then here the 16s cancel and I just have 144. And again, I want a 1 here, so divide everything by 144. And I get x minus 4 squared over 16 minus y plus 1 squared over 9 equals 1. Now I know the transverse axis is horizontal because the x term is the positive term. The center is 4, negative 1. Now, let me see, what do I got on the back here? Do I have another? Oh, we're going to switch to parabolas. I just want to mention, if the y squared term is first, you have to be really careful not to take the number paired with y and put it in the first spot over here because you see it first. It's always the number paired with x. For example, kind of getting off track here, but say it's y plus 10 squared minus x plus 2 squared equals 1, something like that. The center then, people tend to mess this up because they look at this first, they say negative 10, negative 2. It would actually be negative 2, negative 10. That's what I'm talking about. Whoops, negative 10. So be very careful that you get these in the right order. Whatever's paired with x goes first, whatever's paired with y goes second. Something to watch for there. Okay, so back to this problem. This center is 4, negative 1. And then we look at, okay, well, the transverse axis, goes parallel to the x-axis because x is the positive term. So we count out 4 units, 1, 2, 3, 4 in either direction. These are the vertices, so let's go ahead and write those down right away. Vertices are 8, negative 1, and 0, 1. Probably should have put that one first, but it doesn't really matter. So I write them as 2 separate points if I can actually, calculate that easily, but if I'm adding and subtracting an irrational number, I'd probably just write it as 1. Okay, now I'm going to use those other the plus or minus 3 from the center. That will help me get my box so I can find my asymptotes. So those are, again, that's not really part of the graph. That's just a tool to help us get the correct hyperbola. So our asymptotes go through the corners of the box just as before. And then because the x-axis is a positive 1, the hyperbola is here. If it were the y-axis, of course, it would be here, but that would switch the vertices. So we've got this. The main thing on these is not mixing up, which way the branches go, and getting the center in the right spot that this isn't flipped around. So there's our graph. We asked for center, vertices. We still need to find the foci and the equations of the asymptotes. So the foci, remember we add these two numbers when it's a hyperbola. So you always do the opposite operation of what you see here. So 16 plus 9 is 25. So c equals 5. So you're going from the center, count 5 units. You should end up, again, it should be in the cup of the 2 branches, not inside of the box. So this is I'll call this one F1 and this one F2. Because 5 is a whole number, I actually will state these as 2 separate points instead of using plus or minus. So foci 1 is 9, negative 1, and foci 2 is negative 1, negative 1. That's what I labeled F1 and that's what I labeled F2. And then the asymptotes. So you have y minus, the y coordinate is negative 1. So that'll become actually plus 1 equals plus or minus. Just do one statement with a plus or minus. The slope is up 3, right 4, so 3/4. And of course, this is the one with the positive slope and this one's the negative slope. But they both go through the same point. That's why you can write this with just one equation. So use the h that pairs up with x and the k pairs up with y. Plus or minus 3/4 are the 2 slopes. That's it. The hardest part here, of course, getting this done. Just making sure you're careful. And usually if you do this right, you get nice numbers where it makes sense. There can be cases where these things don't cancel nicely. that might happen in your homework, but like on the test, that I'll give you really nice numbers to work with, okay? All right, next is we have parabolas. I think I'll take a little break here and make this a separate video. I can't tackle this last thing, but just like before, if you can do parabolas with vertex at the origin, this isn't really any much more difficult.